Now we have our second keynote. So, first of all, I have to say good morning, Prof. Robinson. How are you? Okay. So today we have a keynote from Professor Dr. Robert Robinson. He's actually retired from Australian Nuclear Science Organization, and he's very much involved in the Asia-Oceania Neutron scattering session. Okay. And then he's for the 2021 been nominated to the AONSA Prize 2021. Congratulations, Prof. And then before he start his presentation with okay. So Prof. Robinson received his PhD from Cambridge University, working with the Professor J.F. Squires. Then he joined the Los Alamos National Laboratory in 1982 as the postdoctoral research fellow. He was then promoted to a technical staff member at the Los Alamos National Laboratory in 1985 and stayed there until he moved to Australia in 1999, where he was appointed to the Australian Nuclear Science and Technology Organization to lead the neutron scattering and synchrotron radiation research. And Prof. Robinson established the Bragg Institutes at ANSTO in 2022. Okay. And serving as a head until he retired in 2016. So for his seminal achievement in neutron science, he received the following awards: Fellowship of American Physical Society in 1998, Fellowship Australian Institute for Physics 2003, Australian Nuclear Association Award 2014, Australian Neutron Beam Users Group Career Award 2008. This is just some of this his achievement. And really for the MNS, we have very strong, and then with the AONSA, thanks to Prof. Robinson to assist us in way to get the power. I'd like to invite Professor Dr. Rod Robinson to deliver his presentation. Prof, the word is yours now.
Hi, everybody. It's a great pleasure to join you. I wish I could do it in person. I haven't been on an airplane for 2 years. So, but maybe one day I could come to Johor and see you all in person. Hopefully not too far away. Okay, I'll switch to my presentation now. Let me figure out how to do this. How's that? All okay?
Okay.
Okay.
Okay, good. All right. If there's a problem or you can't hear me or have any questions, please please interrupt. So look, I didn't really know what to talk about. There's so many things. Maybe this is too introductory and simple for most of you. It's a lecture that I initially gave about 4 years ago in Hong Kong, and I've also given in Japan and in Italy, where I've sort of had adjunct professorships and fellowships. So anyway, I'll just start from the beginning. And in nuclear, I mean, one of the things that, you know, everything we do is based on this curve, which was sort of all sorted out in the 1920s or 1930s. So this shows the binding energy of the nuclei going across the periodic table. I'm just moving my picture out of the way so I can see. And as we all know, the most stable nucleus is iron, right here in the middle. And, we get more energetic nuclei if we go towards uranium and the transuranics on one side or down to the light elements on the other side. And so nuclear reactions occur when we move along this curve in one direction or the other, all right? And so the nuclear reactions that we use to make neutrons are, well, there are a number of them, but I chose 3 here. The main one we have used is fission, for instance, in a reactor where we take, say, uranium-235 and we split the uranium into 2 more or less equal sized parts, and we go over from here to here. It's okay? You okay?
Okay.
And and look, you can see from this, you get a fair amount of energy out of this process, all right? Another one I'm going to talk about is spilation. And here what you do is you basically fire a proton beam into any heavy element along here, and you boil off some neutrons, a few neutrons, and you just move a little bit along here. So you move a little bit along here, but you don't release much heat or energy. And and finally, we all know about fusion, where we take hydrogen or deuterium or tritium, and we fuse two nuclei together, and we make a big jump up to here to helium or something like that, and you get a lot of energy out, all right, that way. So these are the nuclear reactions that you can use, and all of these give off neutrons. And there are some others which are of lesser importance. So fission is what we use in reactors. It also occurs in some lab sources. So if you buy yourself a Californium source from Oak Ridge or somewhere, or from the Russians, that fission occurs in a fixed source. I mentioned spilation. There are actually some other accelerator reactions you can use, gamma-N reactions or deuterium-lithium reactions, which people use in smaller accelerators, fusion. And then, of course, finally, the neutron was discovered originally by bombarding alpha particles into beryllium and knocking neutrons out of beryllium in a lab source. So that was used until the first accelerators came along, and then reactors, but it's not of much interest these days. So nuclear fission looks like this. You take your uranium-235 nucleus, fire, and the neutron comes in, you get an excited state, it splits in two, and you get, 3, 4, whatever, neutrons come out. So you go from having 1 neutron, and these excess neutrons we can use either to irradiate things or in beams. And, and not only that, they can go in and cause multiple reactions, one after the other, a chain reaction. So typically reactors are continuous things. It's a bit like they called them a uranium burner originally. It's just a thing that sits there cooking like a fire, all right? And so typically that you run that at a steady level, but you can pulse them, all right? So there's this case in Russia, IBR2 in Dubna in Russia, where big piece of the reactor rotates around and it pulses on and goes on and off. Or you can do it one-off with a trigger reactor as well. But so reactors typically are steady state, but you can pulse them. And I should say a little bit about the difference between power reactors and beam reactors. So I worked all my career with beam reactors, but a power reactor is something quite different. So a typical power reactor, like a pressurized water reactor, will be about 6,000 megawatts thermal. So that's a lot of energy. It runs at well above the boiling point of water at say 300 plus degrees C. So that's why it has to be pressurized to keep the water liquid rather than being steam. You have a large core. It's very big. It's a great big thing. And the fuel is typically uranium these days, uranium dioxide. And I'll explain why, but it's enriched to a few percent in uranium-235. You can't run a light water reactor with natural uranium. In contrast, a research reactor for beams or other purposes is much smaller, only 300 times smaller, and it's about 20 megawatts thermal, and it doesn't run very hot, only just above room temperature. So it's not very, you can't make steam with this. You know, you're not going to make any electricity with this. It has a small core, only, you know, well, a bit bigger than my hands here, but about the size of a garbage bin, you know, at your house. All right, so not very big, and it's a high density core, so it's a higher density material than uranium dioxide, and it's more strongly enriched than in a power reactor, but what we call low enriched uranium, so that's up to 20% U-235. Right, so this is a limit. You know, if you stay below that limit, it's difficult to then take this material and turn it into a bomb. So there are restrictions. It's easier to have uranium below 20% than above 20%. So that's the difference between power reactors and beam reactors. And here's a picture of our reactor while it was building. So this was back in 2003. And the reactor is going to sit on here, and here's some of the piping. You still have to cool this thing, even though it doesn't run very hot. You've got to cool it quite well. And then there's a storage pond goes here, and then you can see out here this land was all cleared for where the experiments are going to go in a big sort of warehouse-like structure called a guide hall. This here is the concrete pump that was used to pour all the reinforced concrete for the reactor. And then here we are a bit later. This is August 2003, and by now they've got up to the pool level here. So, but the roof is still not there, and they haven't actually poured this floor. But this is where the reactor floor level. So the pool goes in here, and the storage pond for, you know, spent fuel and other things goes here. And then out the back, you can see where this guide hall is going in. They put the crane, they put the steel structure in on one side, and the crane rail on one side, and these are some lab buildings on the one side. So this is fairly typical. And then you go a little bit later to March 2004. Now the roof is on that guide hall. All right, that's all finished. They built the main reactor building up a bit higher, but they haven't put the crane in yet. And I don't think they'd even put the guts of the reflector vessel for the reactor in there at that point. And they certainly haven't put the roof on. All right, so that's just a brief introduction to reactors and beam reactors, research reactors. The other method you can use is spilation. Here you take a beam of high-energy protons and you fire them into a heavy metal target, which could be clad tungsten or liquid mercury. That's what people use mostly these days, but they have also used tantalum, lead bismuth, eutectic, and even depleted uranium. Now, spilation is actually more heat efficient, as I pointed out at the beginning, per neutron. For each neutron you get you get much less heat. So if you want to make steam, this isn't good. But if you want a bright neutron source and you don't want to have to get rid of the heat, this is good. All right. So, and it's more heat efficient than fission by around 20 times. All right, so if you want to make a very bright source and the main problem is getting rid of the heat, spilation is 20 times better. Now, it's not quite as simple as that because you have to cool your target, this heavy metal target, and, you know, maybe with water or heavy water. And you also have to put some container in there that's not a good neutron material, some stainless steel or Inconel or something to contain it all. So in an engineered system, it's about a factor of 10, not 20. All right, but it's still more heat efficient than fission. So what this tells you, this factor of 10 tells you that when people talk about a megawatt spilation source, that's roughly equivalent to a 10 megawatt reactor in terms of time average flux. But most spilation sources are pulsed in time. Typically, a short pulse every 20 to 60 times per second. All right, and they are driven by pulsed accelerators. So it could be a rapid cycling synchrotron, which is what the new China Spilation neutron source has, what ISIS in England has, what J-Park in Japan has, or it could be a LINAC plus a storage ring, which is what the American facilities like SNS and Lance have. All right, these are all circular machines. All right, and so what you do is you pile up your protons in in the circular machine, and then you spit the whole lot out in one go onto the target, and the pulse length that you get is characteristic of the circumference of the ring. So, you know, that's going to be, you know, of order 100 meters. And what that tells you, just to move this, what that tells you is the proton pulse length is typically around a microsecond. If you just take the speed of light and divide that into, you know, the distance, that's what you get. And it's not quite as simple as that for the neutrons, because the neutrons then have to moderate. So that 1 microsecond gets spread out by the moderation time. Now, if you don't have the ring, a linear accelerator on its own gives you about a millisecond in pulse length, or maybe more. And this is what's going into the European spallation source in Sweden. And it's even more complicated in that the accelerators don't have to be pulsed. If you have a big cyclotron, that will give you a continuous beam. For instance, like, it's still a spallation source, but it's continuous, like the SynQ source in Switzerland. But for us as users of beams, it's pretty much, you use it like a reactor. It's the characteristics are very similar to the reactor. All right, and spallation looks like this. Here, you know, it's an old slide, but you take 800 MeV proton, fire it into tungsten. You get, you know, excited states, evaporate off some neutrons, see a lot more than 3 here. And the higher the energy, the more you get out. And then you actually get some secondary reactions, and they release neutrons as well. All right, so that's why you get so many more than the 3 with fission for each proton that you put in. And the target, you know, it might look like this. This is the target of the J-Park spallation source in Japan. So this, I think, is an Inconel container, and inside it's got liquid flowing mercury pumped through it. There's all the pumps and stuff is in this trolley here. So this is sort of the equivalent to the fuel in a reactor. And then the proton beam comes into this window along the front here. But nuclear physics goes on with megavolts, as you know, mega electron volts. And we want to study materials, we want milli-electron volts, not mega electron volts. So we've got to change the neutron energy by 1 billion times, by a factor of 10 to the 9, right? And we do that with moderators. So fission produces an energy of about 2 MeV per neutron. Fusion would produce 14 MeV. Spallation can go to very, very high energies, up to the proton energy, up to a GeV, you know, which actually can cause you shielding problems. Excuse me a minute. So people talk about fluxes and power levels for reactors and spallation sources. Typically for a reactor, people talk about something called the unperturbed thermal flux. This is what you would get out of the reactor if you had no holes in it. So you had no beams and no cavities in it for, you know, a cold source or something like that. And, you know, for a typical 20 megawatt reactor, you will get 4 times 10 to the 14 neutrons per square centimeter per second. The best beam reactor in the world in Grenoble produces 4 times that. Okay. But in the beams, we get a lot less, right? So the neutrons, like, you know, they're very hard to steer or focus or anything like that. So they come out in all directions. And the beam only takes a small range of angles. So typically, the flux in the most you can get in a beam is about 10,000 times smaller than this. So the best beams are about 10 to the 10 neutrons per square centimeter once you're outside the reactor. Pulse sources, you know, they're actually, because the pulse is on for a short time, you actually then think about the peak flux. So for the IBR-2 reactor in Russia, its peak flux is up at 10 to the 16 during the pulse, and then it's off. And that's equivalent to, you know, almost 2,000 megawatts in the pulse. And of course, you can't cool that continuously, which is why they pulse it. Spallation sources, they tend not to quote it this way. They quote the power in the proton beam. And that's simply the product of the current and the energy of the protons before they hit the target. So 100 microamps of protons at 1 GeV will give you 100 kilowatts average power. And a megawatt would be a milliamp at 1 GeV. All right. So when they talk about that, that's what they mean. Now, to moderate, we've got, these are the sort of some of the materials you might use, whether it's a power reactor or a research reactor. You might use graphite or water, like in a pressurized water reactor, or heavy water or beryllium. Now, water's great. It scatters brilliant. This number's big, all right? So that's why it's very good as a moderator. But if you look at how much it absorbs, it also absorbs a reasonable amount, all right? And what really matters is the ratio of the two, all right? So that's what you get. The ratio of those two cross sections of water is 250. If you go to graphite, it's much better, all right? And heavy water, better still. And beryllium's not too bad. And in fact, this is to the point that you can build a reactor just with natural uranium and run it with graphite or heavy water, and you can go critical and you can have a reactor like that. Whereas with heavy water, you can't. You have to enrich. You have to get some more uranium-235 in to even make it go. All right, but the best material we've got as a moderator is heavy water, right? And so most really good beam reactors, high flux sources, are heavy water reactors. And if you want cold neutrons, liquid deuterium is the best moderator for the same reason. It's just the ratio of these, the scattering and absorption cross sections. But because it scatters less, that means the neutrons have to go further before they collide again, and they can lose some energy. All right, so everything becomes bigger. So like a CANDU power reactor is going to be much bigger than a pressurized water reactor. And a liquid deuterium cold source is going to be bigger than a hydrogen cold source. And the other thing, of course, is then the moderation times are longer. So if you want very short pulses, hydrogen is going to be better than deuterium if you have a pulse source. So people to try and change the spectrum, people put sources into a reactor. So most beam reactors these days will be built certainly with a cold source and maybe with a hot source. So if you put a block of graphite in your reactor, it will, close to the core, it will naturally heat up to around 2000 degrees C, and then your neutrons will come out with this temperature rather than, room temperature. And the reactors in Grenoble and Munich have such a hot source. Cold sources are more common. The opposite occurs. If you have a bottle of liquid hydrogen at, say, 20 Kelvin, then you go the other way and you lower the energy the neutrons come out. So people use hydrogen, and there's a question whether it's boiling or supercritical, and you can make it pure parahydrogen, which is good, or in the case of deuterium. So deuterium is better, and that's what's used in Grenoble, PSI, in Munich, and at ANSTO. And people have used methane, it's both liquid and solid methane, but they have some problems. So the spectrum that you get out of a moderator is, if it's really just the neutrons are a perfect gas in thermal equilibrium. So if you have a very big moderator, perfect gas in thermal equilibrium, this is the spectrum that you'll get. And this is basically the temperature, KT, right? And I'll show you some curves of that in a minute. So the spectrum you get depends. It's called the Maxwell-Boltzmann distribution, all right, in classical thermodynamics. On the other hand, if you're not in thermal equilibrium, so if you put in very high energy neutrons, like for our megavolt neutrons from nuclear reactions, and there's not going to be much upscattering. Everything's going to be cooling down or slowing down. You get a 1/E spectrum like this, and so this is sometimes called a 1/E or slowing down spectrum. All right, and you get this at spilation sources. You get it at reactors as well, because you're putting in high energy neutrons. So the sort of curves that you get look like this. So the Maxwellian gives you this bump here, all right, bump here, and so this is room temperature. If you go to the graphite 2000 degrees, you move the curve to the right. If you go to cool it down, but with liquid hydrogen, you go to the left. So if the science you want to do is down here in the millivolt range, a few millivolts, all right, which might be tens of angstroms in wavelength, you're going to be, 30 times better with a cold source in your reactor. And you look at that, okay? And so that's for reactors, and it's similar for spilation sources. It's the moderation is the same, but you get a longer tail going to higher energies, and you can clearly see this 1/E. So this is a log scale. You can see this 1/E spectrum here. It's there in the reactor spectrum as well, actually, but not quite so obvious. So this is what this is a section through the vessel, if you like, of our reactor in Sydney. And this is the concrete shield out here. So all this metal stuff, concrete. Then there's a swimming pool reactor. So this is water. Then there's a vessel with heavy water in it. And in the middle is the core with the fuel. All right, the fuel's here. It's just 4x4, 16 fuel elements. And then the neutron flux spreads out in this reflector vessel. And we look, this is our source right here for thermal neutrons. And then for cold neutrons, this is where our bottle of liquid deuterium sits, right here. And then the beams go out through these tubes and then into what are called neutron guides, through shutters, and then out to the experiments. Okay? And the cold neutron source looks like this. This is an aluminium alloy container, multi-skinned, and it's filled with, because you've basically got this thing sitting at 20 Kelvin, about a meter away from something producing 20 megawatts. So it's got to be well insulated. So this is filled with liquid deuterium. Ours actually has a cavity in it. And that's what the neutron beams look at for the cold source. And the spectrum, you know, is there where I said about 10 to the 10, all right? Neutrons per square centimeter second. And then, so here's a picture of the reactor, if you like, the shell of the reactor. So this is all heavy concrete. And I'll have to move picture here a bit. So you can see where some of the beams come out here on one side, and then on the other side there's a bunker, all right, that goes out to the experiments. This is inside the bunker, and the guides come out like here. So these are the stainless steel vacuum jackets for the guides. So this is like an optical fiber carrying the neutrons out. Inside it looks like this. So here's the vacuum jacket, then you've got some glass, a glass box with float glass, very smooth glass on the inside, and then fancy metal coatings on the inside of that, and inside vacuum. So it's a flight tube with vacuum, and it's actually curved along the length, so you can't see straight down it, but with reflections you can. So this we use to carry the neutrons away, and these are typically about 5 centimeters across, up to 30 centimeters high. And here's a shutter, all right? So we replaced the shutter in 2012, and they've just done another one earlier this year, and it's complicated because it's got 4 guides. You see here all the glass, 4 guides all together going, and then this is the rotating shutter, and this is the piece that goes upstream of it. All right, so that's what that looks like. And then going out into the guide hall, you get something like this. So these are this is the picture from Munich in their reactor. So the guides are coming out of the reactor, and then the instruments or the experiments are on the end like this, and then some of them are not so obvious, all right? A few of them come out on the side like this here. And this is what our reactor looked like before we put any instruments in. So you can see the end, we're looking towards the reactor. This is the end of the bunker for thermal neutrons, and there's the end of the bunker for cold neutrons, and the cranes are there for where the instruments are going to go in. They're all there now, but they weren't when this picture was taken. And that's more or less what it looks like now. This photograph's a little bit old, but you can see 2 big small angle scattering machines here in the corner. There are 4 diffractometers over here. There's a reflectometer there, some other instruments up there. They're not very obvious. All the equipment for changing temperature and pressure and so on, magnets and so on for the experiments are here, and then some labs over on the side. So all I've talked about so far is just the spectrum of neutrons you get out of the reactor. But to do a real experiment, we want to know the energy of the neutrons or the wavelength, all right? And there's basically two ways that you can determine that. The first is you can diffract from a crystal or reflect from a crystal face like this. So the neutrons come in, they reflect from the crystal. These are the rows of atoms. And, depending on the spacing between the atoms, you get constructive interference or not. All right. And so what this will do is if you put a polychromatic beam in here, it will send out just one wavelength with this wavelength according to this formula. So that's a way of specifying a particular wavelength, and you can do that with X-rays as well. It's the same physics. Or the other way is by measuring the time. If you've got a pulse of neutrons, you can just measure the time. You know how far they've come from wherever the source was, and using the de Broglie relation, you get this formula where the wavelength ends up proportional to the time over the distance. All right, so that's called time of flight, and we use both of those methods. Here's an example. The crystals aren't actually on it, but this is what a crystal monochromator put the graphite crystals on these blades. So a modern one, it's not just one crystal. I mean, here we've got 9 of them, all arrayed on these aluminium sheets here, and all driven with motors and everything. So they focus, but you can see how they're at an angle. They focus horizontally, and then they can also they're on a mechanism here, so they focus vertically as well. So that's what a modern monochromator would look like. So if I first talk about diffractometers, you can do it 2 ways, really. Constant wavelength or angle dispersive, which is very much like an X-ray diffractometer operating on copper K alpha. So then you've got a 1 wavelength and you scan angle, or you can do time of flight where you pulse the beam, and then you go wavelength dispersive. You have a fixed detector, you don't have to move anything, and you just scan the wavelength. Right? Those are basically the 2 methods. So if you have a neutron beam coming in, you monochromate with this crystal, go to your sample, you get diffractive peaks here, you pick them up in all these detectors. They've all got their own collimators, and you have to move this around a little bit to fill, so that you get a continuous pattern. And that's what it looks like. This is the one at NIST in Washington, D.C. It's quite an old machine. So the reactor's over to the right. It comes out here. The monochromator's in the shielding down here somewhere. The beam comes here. Here's the sample, I think in a cryostat or a furnace, I'm not sure which. And then the detector bank is here, right? So that's what we do. And our machine in Australia is very similar. And if you go to the ILL, it'll be similar there, all right? This is our collimator box for our diffractometer here, all right? So very nice, all, and we had 128 detectors behind this. This is before it was installed. And if you do it by time of flight, the neutron beam comes in from your pulse neutron source, the sample is here, and then you have an array of detectors here. The best ones are in backscattering, and you just pick up the signal. Nothing moves. And it just measure as a function of time. So you need fancier electronics to do all of this, but we know how to do that now. And this is what a modern powder diffractometer looks like. This is the one near Hong Kong, in China. So here's the Spilation source target station. The moderators are in here right in the middle. Your neutrons fly out through a vacuum tube. The sample's here. The detectors, it all looks very boring because it's just lots of shielding and you can't see any of the details. But it looks very boring, but it works quite well. And if you want more intensity, you can get rid of the collimator and get a very, very good detector. This one has about a square millimeter resolution. And you just sit there and count. It's just like film, electronic film, but you can't get quite as good resolution as you do that. So this is Wombat in Australia, but there's a similar machine, D20 in Grenoble, and you can do similar things. For instance, GEM at the ISIS Spilation source can do similar things. I think I'll skip over that. So look, the other main methods are for looking at nanostructures. And the 2 methods are small angle scattering and reflectometry. So, and what we want to look at is things on the scale of 1 to 100 nanometers, 10 to 1,000 angstroms. Now, if you take this formula here, Q equals 2 pi over D, and there's the Bragg relation. If you want D to be much bigger, going up to from an angstrom to 10 or 100, you want D to be bigger. It's in the denominator. We want lambda to be big and theta to be small. So we want small angles and long wavelengths, which is cold neutrons. And we use these methods to study whole proteins, whole polymer molecules, microphase separation, defects in metals, vortices in superconductors, pores in porous materials, skyrmions, which are very fashionable now for magnetic storage and things like that, and coatings, nanoscale coatings and interfaces, right? So the experiments in principle are very similar. In sands, but we typically have a transmission geometry, whereas in reflectometry, we have a reflection geometry from a smooth surface. In sands, we use a pinhole, and in reflectometry, we use a line geometry, right? Because the surface is flat, we can use a line. We use slightly coarser resolution for small angle scattering, about 10%, and a big 2D detector. I'll show you some in a minute. And reflectometry is slightly better wavelength resolution and a smaller detector. So here's the SANS machine at the China Spilation neutron source near Hong Kong. And again, it doesn't look very complicated, but here's the sources over here. You come here, the sample goes here, and then the detector sits in this vacuum tank here. All right, and it's a very simple experiment. You just need source, collimator, sample, detector, really. It's a very simple, conceptually a very simple experiment. And here are the components of our first one in Australia. This is the thing that gives you the 10% bandwidth. This is the rotor for the velocity selector that gives you, so crystals give you too good resolution. You don't want, so you use this thing called, it's like a turbine, that the Archimedean screw that the neutrons can go through. It's absorbing plate. So this thing spins, and depending on the speed, that gives you the wavelength that you use. So that sits in this blue box here. And then you have apertures in this evacuated box, which isn't fully installed yet. So there's 20 meters of this, and then another 20 meters of vacuum vessel, all right? And the detector sits inside this. So this was actually when it left the factory in Melbourne on the way up to our reactor, came as one piece. And here are our two SANS machines with the back off them open. So there's one type of detector in one and another type of detector in the other, all right? So this one's a 40-meter SANS, 20 plus 20. This is a 35-meter SANS. This one's time of flight with choppers. This one's constant wavelength. So everything I've said so far has assumed no change in the neutron energy at the sample, as in X-ray, as we're assuming. It's often called elastic scattering, but it's really total scattering. Now, normally the elastic scattering is much stronger than the non-elastic or inelastic scattering, so this is reasonable to assume it's elastic, but it's strictly not. But if we measure both the instant energy and the final energy separately, we can actually measure the inelastic scattering as well. So there's another set of spectrometers that we use to do that, and I won't go into all the details, but basically I told you you've got these two methods. You've got to determine EI and F, and you can use crystals or time of flight in any combination. So crystal, time of flight, crystal. So if you just use crystals front and back, this is as in a triple axis spectrometer and typically the reactor. If you use time of flight throughout, that would be like in a chopper spectrometer. And, you know, it's used a lot at spilation sources, but also at some instruments at reactors where you have a set of choppers. You need more than one. And then the other is where you use a crystal and time of flight, and a few very good instruments at reactors. Our own Pelican in Australia and AONSA at the ILL do that. Or you can do the other way. It's called inverted geometry, where you have time of flight and then you get the analyze with the crystals after the sample. So this is inverted geometry, and that's typically done at the spilation source. So the Tosca instrument analysis or DNA at JPark, which is a backscattering spectrometer. Here's a triple axis spectrometer schematically. All right, so you come out of the reactor, there's a crystal here, sample, you go to the sample here, another crystal set at a different setting and out to the detector. So you measure EI with this angular setting and EF with this angular scattering. And the components look like this, right? This is sort of, they all move around on air pads on a polished floor. So this was in the factory for where they made all these stages, but that's what they look like. So look, just to look at the fleet of instruments we have in Australia, we have 4 diffractometers here, 2 SANS machines plus an ultra SANS machine in here, 1 reflectometer, and there's another one gone in here now actually, so there are 2. A couple of spectrometers, cold neutron spectrometers here, they're quite big, expensive things. 2 triple axis spectrometers, 1 built by Taiwan. And I haven't talked about this at all. This is neutron imaging. So just the neutron equivalent of CT scanning like you have in a hospital. All right. So, but we typically do it on, we don't do it on human beings or even animals, we do. But we might look at fossils or engineering components. And in Japan, at the J-Park spallation source, which is the best we have in our region, they have, 23 beamlines here, all doing similar but different things. All right. So that's what they've got. And now just to summarize, here's a table which I hope you find useful of some of the leading reactor sources. All right, so in Grenoble, Munich, Washington, us in Sydney, Korea, China, Oak Ridge. All right, and they've all got cold sources and they've all got guide halls like I showed you with various different powers, but you can do a lot with 20 megawatts like we have, or like NIST is up here, we're down here, Opal, yeah. And then there's the pulsed reactor from Dubna, all right? The 1 pulsed reactor, but most reactors are steady state. And the leading spallation sources, well, today the leading ones are in Japan at J-Park and at Oak Ridge in the United States, which Oak Ridge is now 1.4 megawatts and will go to 2 megawatts soon. So they're probably the best. This one's very good too, not as powerful, but they've been doing it a long time. And the newest is in Dongguan near Hong Kong in China. This is just starting up quite well. The long pulse spallation source being built in Lund in Sweden, all right, which is slightly different. And then the continuous spallation source that I mentioned, Syncue in Switzerland. And I think that's the end of my talk to fit in the half an hour you gave me. So I'll finish there, and I'm very happy to take any questions. Oh, was I too fast?
Thank you, Robson. So I think I may allow one question from the audience. Is it okay, Robson, to have one question?
Okay, no, thank you very much. I'm Yamashita from Japan.
Oh, hello.
I was former director for research department of JAEA.
Yes.
Yeah. After accident of Fukushima Daiichi, yeah, the JRR3 was stopped for 10 years.
Yes.
Now JRR3 has started,
Yes.
yeah, in operation.
Yes.
Please put the JRR3 in your slide in the table.
I should. Yes, I knew it started. Congratulations. At the time that so I first wrote this talk about 4 years ago, and of course you were there, but you were not operating. Yes, of course. I'm sorry.
Yeah, thank you very much. It is very, very so our proud that the JR3 recently started. Thank you very much.
Yeah, no, you're welcome.
Very interesting presentation.
Okay, thank you very much, Dr. Yamashita, for the question.
Yeah,
I should say briefly, we were very happy to welcome people from Japan to Australia. So we offered straight away in 2011 after the earthquake, and they kept coming for a long, long time actually, while JRR3 was down, and there was a wonderful collaboration between Australia and Japan. So I think we all benefited from that. But we're glad. I mean, not many places are running right now because of COVID right at the moment. So maybe JRR3 is, and I'm just doing reviews for Oak Ridge, and they are running. The reactor's running in Australia, but they're not allowed to do science at the moment. But that should change in the next few weeks. But if you look at it at the moment, I think not many places are running well just because of the restrictions on people moving around because of COVID.
Yeah, thank you very much then.
So that's my last question for you, Professor Wilson. Recently, I got email regarding the news that the Australian government will spend some money on the new facility for radioisotope. So what is your comment?
Oh, yes. So look, so our reactor's a multi-purpose reactor. I mean, it really has 2 or 3 purposes. So we produce molybdenum-99, and its daughter is technetium-99m, which is used for medical imaging. And we've been doing that for a long, long time in a facility that was built in the 1950s and has all sorts of problems, reliability and safety problems. And so there's been a push for quite some time now to replace it with a modern facility. All right. I mean, there's 2 parts to this. First, you have to separate the molybdenum-99 out from the uranium material that you use. So that's a sort of wet chemistry process. It's a bit messy, actually. And so we've already got a new plant to do that. And then you take that molybdenum-99 and you have to put it into a little machine that can go to the hospital called a generator. And you might want to prepare other medical isotopes as well. And that's done in a different, so the first part is sort of like a bulk chemical process. And the second one is actually preparing everything so it can go to a hospital or a radiopharmacy. And it was time to get a new, if you like, factory to do the latter. And that's the money that's just been approved. Well, it's not, there's money for design. All right, they haven't actually got the money to, haven't got the money, as I understand it, haven't got the money to build it yet, and they're looking for private sector involvement. So we watch this space, but it's basically good news. Look, the other big piece of good news I heard in the last week is that the South African government is giving money for them to build a new research reactor just outside Pretoria, both for radioisotopes and for beams. And I imagine they're going to do something very similar to what we have done in Australia.
Okay, thank you, Prof. So I think if I have a chance to get the visas, so we will see you in Buenos Aires, Argentina.
I hope so.
Okay, and have a good luck for your new facilities in Opal. Okay, thank you. So
well,
thank you very much.
Thank you very much.
Okay, so I hope everybody will enjoy the Prof. Robinson presentation, and I hope for the young students, young researchers, please keep in touch with Prof. Robinson for the using the other regional facilities. Thank you again. Bye.
You're welcome.